Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my third video on the Millennium Prize Problems. I think I mentioned in a few other videos that there's 7 of these problems known as Millennium Prize Problems. One of them's already been solved, but the remaining 6 haven't. They were all proposed in the year 2000. That's how they got their name. And for the 6 that haven't been solved yet, anybody who can solve them will get $1 million, $1 million prize. They're considered, 6 of the most important unsolved problems in math. And today I want to talk about one of those problems, namely the Birch and Swinnerton-Dyer conjecture, and I'll get into what that is in a minute. Just suffice it to say for now that this conjecture pertains to elliptic curves. I did make a video on elliptic curves a few months ago. In case you guys aren't familiar with them, they're very important. They're a very important class of curves. They're not to be confused with ellipses. They really have very little to do with ellipses. This picture on this slide shows a picture of an elliptic curve. They're actually cubic curves. They have degree 3. And they have an important group law associated with them. I'm not going to go into too much detail about elliptic curves in this video, just enough to explain what this problem says. Anyway, let's begin. So here's what the Birch and Swinnerton-Dyer conjecture says. And I'm not going to go through this slide in detail because it's a very, very complicated, even the statement of this conjecture is very complicated. I believe it was first proposed sometime in the 1960s. I actually think it's one of the more recent unsolved Millennium Prize problems. I actually thought I might be able to solve this about maybe 5 or 6 years ago. I remember, trying to learn as much as I could about elliptic curves. I already knew a fair amount, but I was trying to learn more. I was going through an undergraduate text. I think it was by Silverman and Tate. And it was a very, very complicated text. I think it's a lot higher level than undergraduate level because I have a PhD in math and I couldn't even get through the whole book. I kind of stopped halfway through the proof of Mordell's theorem, which is kind of just a basic theorem involving the rank of elliptic curves. So I didn't get very far with it, unfortunately. Um, so no $1 million prize from me. Anyway, I'm going to start with some background because, like I said, this is a very complicated conjecture. So I'm going to start by first defining what elliptic curves are. I did this in another video, but maybe you guys haven't seen that video. Elliptic curves, like I said, they're cubic curves, but they're a particular type of cubic curves. They have a standard form which is called the Weierstrass form. It's y squared equals x cubed plus ax plus b, where a and b are arbitrary, I guess, complex numbers or real numbers, depending on the field you're working over. You can define elliptic curves over arbitrary fields, it turns out, finite or infinite. Most common field, people study them over the real numbers, but you can also study them over the complex numbers or over finite fields. And it turns out there's finite fields with any prime number of elements or any prime power number of elements. So those are some fields that people study elliptic curves over. And if you want to know what they look like, there's pictures of several different elliptic curves on the right. These are different values of A and B, so you get different kinds of behavior depending on the values of A and B. Sometimes they have 2 pieces. If you have 2 pieces, the piece on the left, which is a closed piece, that's called the egg of the elliptic curve. And then there's some other types of elliptic curves with just 1 piece. And there's also degenerate cases where you have a cusp, but those aren't considered elliptic curves if there's a cusp. Those are considered singular elliptic curves, but they're not considered elliptic curves. So that's kind of what they are and what they look like. And they're very, very important. And one reason they're important, it turns out you can define a group. You can define a addition of points on elliptic curves. And here's how you add 2 points on an elliptic curve. So imagine you just take 2 arbitrary points on this elliptic curve. Let's call them P and Q. Well, since this is a cubic curve, it turns out there's a theorem, I think it's called Bezout's theorem, that says that if you intersect a line with any cubic curve, it doesn't just have to be an elliptic curve, but any cubic curve, you always get exactly 3 points of intersection, counting multiplicities, also possibly counting the point in infinity. Uh, so here's an example. Here's an example of a kind of a typical line intersecting a typical elliptic curve. And we started with the points P and Q. These, what I said, were kind of arbitrary, distinct points on this curve. They don't actually have to be distinct. If they're not distinct, you take the tangent line. And then whenever you do that, you always get a third point, which we're calling R here. R is the third point on this line that intersects this elliptic curve. And to add the points P and Q, we can define addition of points on the elliptic curve. The way we do that is once we have R, we reflect it about the x-axis. We find the other point intersecting the elliptic curve with the vertical line passing through R. And since, and if the elliptic curve's in Weierstrass normal form, that means it's always symmetric about the x-axis. So that's just going to give us the reflection of the x-axis of the point R, and we call that. Actually, we called it. I made a mistake earlier. The third point on this line is minus R. So to get R, we have to reflect it. So R, which we call P plus Q, there's two steps here. First, we find that third point on the line containing P and Q intersecting the elliptic curve, and then we reflect it about the x-axis. That gives us the sum R equals P plus Q. So that's how to add 2 points on an elliptic curve. And the nice thing about this addition we've defined, it turns out to make the elliptic curve into an abelian group with respect to addition. Abelian group just means it's a group, but it's commutative with respect to addition. I think it's pretty easy to see it's commutative because it doesn't matter which one you add first. I mean, R is the third point on the line containing P and Q. It's also the third line on the point containing Q and P, which implies that Q plus P is the same as P plus Q. So that's why it's an abelian group. And it is a group. It's a little hard to prove that it's a group. You have to prove the 3 properties of a group. The hardest to prove is associativity. But you can do it. It's just a mess, but you can do it. Anyway, so that's what an elliptic curve is. And then one of the kind of fundamental properties of an elliptic curve is what's called its rank. So I just said that the points on an elliptic curve, specifically the rational points. Now we're going to look at the elliptic curve E. So E is an arbitrary elliptic curve. It could be elliptic curve over R over C. Usually you define elliptic curve over the complex numbers or the real numbers. If you want to have the real components or rational coefficients, A and B have to be rational here. As long as A and B are rational. So you have the elliptic curve y squared equals x cubed plus ax plus b, where a and b are arbitrary rational numbers. And then you can define that elliptic curve over any field you want. Particularly, you can define it over the rational numbers, q. So if you define the elliptic curve over the rational numbers, it turns out that over any field, this is another interesting fact, I haven't proven this, but if you define your elliptic curve over any field, f, it doesn't matter what that field is. It turns out that you can still define the group law the way I've described it, and it turns out that that group is still an abelian group. So in particular, it's an abelian group over Q, and it turns out that it always has this form. It's the direct sum of z to the r for some non-negative integer r. R is known as the rank of the elliptic curve, and the torsion part. We call that EQ torsion. And EQ torsion turns out to always be a finite group. I'm not going to explain what EQ torsion is. It's kind of the, I don't know. I don't want to go into this in any more detail, but it turns out it always has this form. There's a finite part which we call EQ torsion, and I think there's only something like 15 possibilities for EQ torsion. It's either a cyclic group of order up to 12. There's no cyclic group of order 11, but you can have cyclic groups order 1 to 10, order 12, or you can have the direct product of a cyclic group of order 2 and another cyclic group of order 2, 4, 6, and 8. Those are the 15 possibilities for EQ torsion. And I've actually done exercises where I've demonstrated that particular elliptic curves have each of these 15 possible torsion parts of the group. Kind of fun exercise. They can be very messy, but they're fun exercises when you start learning about elliptic curves. And then the other part is this infinite part, z to the r. And z is, I guess, z is just the integers. So the z is a group. I mean, it's a group with respect to addition. You can add two integers. You always get an integer. You can check that the integers with respect to addition form an abelian group. That's just z, or z to the 1, if you like. But then you can raise that to any power. So z squared would be the group corresponding to lattice points in 2 dimensions with integer coordinates. Z cubed would be lattice points in 3 dimensions with integer coordinates. We only live in 3 dimensions, but you can imagine any number of dimensions you want. So z to the r, if you like, is a geometric way to think of that. It's the set. It's a group corresponding to the set of lattice points in r dimensions, and r can be arbitrary. Because even though we can only visualize 3 dimensions, we can mathematically define as many as we want. So that's what this means. And R is what we call the rank of the group. And there is a theorem. This is proven. This is called Mordell's theorem. Mordell's theorem says, and I tried to learn the proof. I kind of stopped about halfway through. But Mordell's theorem says that the rank of any elliptic curve is always a finite positive integer, or non-negative integer. It could be 0. There are elliptic curves with rank 0. Um, I think, as a matter of fact, most of them are. But anyway, so that's the kind of what the definition of the rank. But now I have to talk about, that's one part of the Birch and Swinnerton-Dyer conjecture. It's a conjecture about the rank of arbitrary elliptic curves. But then on the other side is there's an equation for the rank of an arbitrary elliptic curve in terms of something else, which I'm getting to, namely the order of the zero of the Hasse-Weil L-function. So now I have to explain this. And I think this might be even a little more complicated than just what. This is not an easy theorem. It's not even an easy theorem to state, unfortunately. But let me just keep going with this. So this function, this is an analytic function. L, it's an example of an L function. There's a lot of different L functions, and algebraic number theory. This is just one of them. And we define this analytic function we call L of E and S. S is just a complex variable. S is an arbitrary complex number. I think this LE of x is an entire function, if I'm not mistaken. And we define it. First, we have to define LP of E and S, where P is an arbitrary prime number. Not quite arbitrary, because P has to be a I think it is arbitrary, actually. Yeah. So there's formulas for LP of E and S for arbitrary prime numbers P. And these are the formulas. It turns out that if first I have to find these number a sub p. These are ugly formulas. Maybe I shouldn't go through this whole thing, but a sub p is equal to p, the number of points on the elliptic curve modulo p plus 1, because you have to have the point at infinity. So it's kind of the number of rational points on the elliptic curve modulo p. And you have to be careful because there's some special cases where p divides the discriminant. You have to worry about those cases. And in those cases, I think AP is equal to either plus or minus 1. Yeah, I can't remember specifically which it is, but I think it's equal to plus 1 if it divides the discriminant but not the square, or maybe if it divides the discriminant amount, the square is minus 1, it's plus 1 otherwise, if it divides the square of the discriminant. Something like that, or if it square divides the discriminant. I don't remember this specifically. You can read it on this slide, but anyway, it's a well-defined number, and that's how we define L sub P of E and S, and then we define L of E as S as just the infinite product over all primes P of the reciprocal of LP of E and S. So that's how you define the Hasse-Weil L function. Pretty complicated definition. But you can do that for any elliptic curve you're given. And now we can state the Birch and Swinnerton-Dyer conjecture. It's abbreviated as the BSD conjecture, by the way. I believe Swinnerton-Dyer was one mathematician. That's why his name is hyphenated, and Birch was another mathematician. These are the guys who came up with this conjecture. So here's what the Birch and Swinnerton-Dyer conjecture says. It says the rank of the elliptic curve, of an arbitrary elliptic curve E, which I defined earlier, is equal to the order of the zero of the Hasse-Weil zeta function L of E and S at S equals 1. It turns out that if the rank, so what this is saying is, for instance, if the rank of the elliptic curve is 0, then the L of E and S is non-zero at S equals 1. L of E and 1 is non-zero. If the rank is 1, then if the rank is greater than or equal to 1, then L of E of S has to be 0. And the order of the 0 in particular is equal to the rank. What that means is, mathematically we can say that L of E and S is asymptotic to some constant times S minus 1 to the rth power. And you can see if R is 1, if R is 0, it's even non-zero at that point. But if it's R is 1, then it's 0 at that point, but it's linear. It's asymptotically or approximately linear close to S equals 1. You can think of this as the first term in the Taylor expansion of L of E and S about S equals 1, if you like. And anyway, so that's what it says. And now I'm just going to tell you some status of the, nobody's proved it yet. But people, there have been mathematicians who've made some progress towards proving it. And I'm not going to go through all of these items on this slide. But here's what has been done. Number 3, it turns out there was a guy named Kohlwagen in 1989 who proved the special cases correspond to ranks 0 and 1. It's known that the BSD conjecture holds whenever the rank of the elliptic curve is either 0 or 1. It's known that if the rank is 0, then the L of E and 1 is non-zero. It's also known that if the rank is 1, that L of E and S near S equals 1 is linear. It's asymptotic to S minus 1. See, some constant times S minus 1. Both of those facts are known. And if you look at this graph on the right, this is a kind of a numerical, it's not a proof, but somebody actually looked at points on this line corresponding to, I guess, values of the L function. And then this red line is what we would expect because we know that the rank of this particular elliptic curve is 1. That's why it's a straight line. And you can see the points kind of give numerical evidence that it seems to be true for this particular elliptic curve. But as you all know, that doesn't constitute a proof. But it actually has been proven. And another item on this, item 5, first Andrew Wiles, I'm sure you guys have all heard of him. Andrew Wiles was the guy who proved Fermat's last theorem, a very famous unsolved math problem that was 350 years old, first proposed by Fermat, who thought he had a proof. He said he didn't have enough room to write it down, but he never actually published a proof. And now we think that we probably didn't because it took over 350 years to prove it. Finally, Andrew Wiles proved it in 1995, but he had to use some math that was very, very complicated. Algebraic geometry, which I never even learned. Very complicated math. He had a 129-page proof for Fermat's last theorem. He did prove it, though. But, one of the he also proved another very important result known as the modularity theorem in 2001. He proved that all elliptic curves over Q are modular. I'm not even going to explain what that means. It just means that there's a connection between elliptic curves and modular forms. Modular forms are another very important area of math. I probably make some videos on them. I haven't made any videos yet on modular forms, but they're pretty cool. They're a special type of analytic function. They have some very amazing properties, and it turns out they're very closely related to elliptic curves. But I'm not going to explain any more than what I just said about that. But it turns out that you can use the modularity theorem plus some other results, which this guy Breuil, I don't even know how to pronounce his name, Breuil et al. I guess he worked with, along with some other mathematicians. What he was able to prove using Weil's result, the modularity theorem, was that in fact um, uh, the Hasse-Weil L-function, L, V, and S, is well defined at S equals 1 for every elliptic curve over the rational numbers. The fact that they're modular means that you can define. It wasn't even known that you could even define the Hasse-Weil L function at S equals 1. So I mean, if you couldn't define it, then obviously this conjecture would have been false. I guess one of the corollary, if somebody proved the Birch and Swinnerton-Dyer conjecture, would be, of course, that the L function L, V, and S for every elliptic curve E is well defined everywhere, in particular at S equals 1. But I guess since we know that all elliptic curves are modular, now we do know that they're well defined, which is a nice thing to know. Finally, the last result, I think this is a pretty important result, and this one was actually discovered pretty recently by Bhargava and Shankar in 2015, I guess less than 10 years ago. What they proved, first they proved that the average rank of all elliptic curves, and I guess you have to define how you're averaging elliptic curves. There is a way to do this in a consistent way. I guess you average all values of A and B in some systematic way. They found the average rank of all elliptic curves is 7/6. It's not even that big. I mean, it's a little bit bigger than 1, which means that most elliptic curves have rank either 0 or 1. And in particular, a finite fraction of them have rank. Here it says rank 0. I think they really mean rank 0 or 1. Kind of makes sense if you think about it, right? I mean, so consider all the elliptic curves of rank greater than 1. Well, if the average rank is 7/6, then all the ones that have rank greater than 1 have rank at least 2. And if it was a proportion that was suppose that the set of all elliptic curves with rank less than or equal to 1 was a set of measures 0. Well, that would mean that the average rank of all elliptic curves would be at least 2, because the elliptic curves of rank 0 and 1 wouldn't have any weight. But the fact that they do, the fact that the average is less than 2 implies that, in particular, the number of the fraction of elliptic curves with rank 0 or 1 is finite. I think you can even bound it better than that. I think it's at least 5/6, something like that. I think most elliptic curves have rank 0, 1. I think I did read once that it's at least 5/6 of all elliptic curves have rank 0 or 1. So that's a nice result, because that's most elliptic curves. Of course, that's not a proof, but what it's saying is that for most elliptic curves, at least 5/6 of them, they satisfy the conditions of the Birch and Swinnerton-Dyer conjecture. So it's true for most elliptic curves. Of course, that's not a complete proof. We need a proof for all elliptic curves, in particular elliptic curves with rank 2 or larger. Nobody's proved it for any elliptic curve of rank greater or equal to 2. Status for any rank grade 2 or larger is still unknown. And even though these are kind of rare elliptic curves, I think there are elliptic curves with ranks known up to like 22. There's some elliptic curves known that with some really huge ranks. I think 22 is the largest that's currently known. It may actually be the largest that exists. I think there are some mathematicians now who think that 22 is the largest possible rank of any elliptic curve. Not only are they all finite, like Mordell-Weil, the Mordell's theorem says, but I think now a lot of mathematicians think they're bounded by some finite value, most likely 22. So anyway, but so even though we don't know anything for rank 2 or larger, we also, there's very good numerical evidence, and kind of like the graph on the right, there's very good numerical evidence, I think, for higher rank as well. I think just about every kind of numerical simulation any mathematician has ever done to try to simulate whether or not the Birch and Swinnerton-Dyer conjecture holds for a particular curve. I think they all show very strong evidence that it does hold. So it's probably true. And as far as I know, I don't think there's any Millennium Prize for disproving the Birch and Swinnerton-Dyer conjecture, because I think most mathematicians want it to be true, kind of like the Riemann hypothesis. And actually, there's a lot of important consequences. There would be a lot of important consequences if the Birch and Swinnerton-Dyer conjecture turns out to be true. If we could prove it, we could prove a lot of other things. I'm not going to go through all the items on this list. There's one I particularly like, the one involving congruent numbers. I think that's the first of these bullet marks near the bottom. It says, for in particular, congruent numbers are a fun thing. I studied them for a while when I was studying algebraic number theory. I can actually tell you what a congruent number is. A congruent number is a positive integer that's equal to the area of some right triangle with all rational sides. And they're kind of hard to find, but for small congruent numbers are pretty easy to find. And actually, one consequence of the Birch and Swinnerton-Dyer conjecture would be that every positive integer congruent to either 5, 6, or 7 modulo 8. For instance, 5, 6, and 7 themselves, that's easy to prove. Or 13, 14, 15, or 21, 22, 23. You could keep going like this, 1,000,005, 1,000,006, 1,000,007 if you like. All those numbers turn out to be congruent numbers, meaning that it does exist right triangle with rational sides with that area. So there is a right triangle with rational sides and area. 1,000,007. I don't know if anybody's ever found one, but there is. At least there would be if the Birch and Swinnerton-Dyer conjecture could be proven. And most people believe it's true, so it probably is. And there's a lot of other important consequences as well. Anyway, that completes my talk for today on the Birch and Swinnerton-Dyer conjecture. Thank you for watching. Long live math, and I'll see you guys next time. Bye.